Oh, hi. So we're going to talk about section 4.3, graphs of exponential functions. Okay. Now, while I go through these graphs of exponential functions, it's really important to me that you understand why they look the way they look. I don't want you guys to get stressed out about, the details of the various graphs. I do want you to understand the trends that occur. So while we're doing these graphs, we're going to be making a lot of comparisons. Okay, so here we go. 4.3 graphs of exponential functions. Okay, so what I would like to do is actually make 3 graphs of exponential functions, and then we can compare them and then talk about various trends that exist. So I want to graph y equals 3 to the x, and we'll do that in one color. In another color, we will graph y equals 2 times 3 to the x. And last but not least, we will then look at the graph of y equals 0.5 to the x. Okay? Alrighty, so now if we don't know how to make these graphs initially, one thing we can always do is go back to the source and make a little XYT table and plot various points. Okay? For example, if we plug in x equals 0 here, anything raised to the 0 power is 1. Okay? Now, we can think in the back of our heads that the general formula for our exponential functions is a times b to the x. Notice here we don't have a number out in front, and we know that number is our initial value. So we can think of this as 1 times 3 to the x. Therefore, this y-intercept makes entire sense. If I plug in x equals 1, 3 to the first power is 3. If I plug in 2, 3 squared is 9. We could keep going. If we plug in 3, we're going to get 27, etc. But I'm too short to graph that anyway. All right, so let's ask what happens if we plug in a negative value. Well, 3 to the negative first power. How do you deal with negative exponents? Remember, to make an exponent positive, you move him down to the denominator. So that's 1 over 3 to the first, or 1/3. If I plug in negative 2, well, 3 to the negative second power is 1 over 3 to the second power, which is 1/9. Okay? Let's make this t-table here. Now, look at this. We know that our initial value is this number in front, which is 2. And notice when we plug in x equals 0, 3 to the 0 power is 1, and 2 times 1 is 2. Okay? If we plug in x equals 1, then we have 2 times 3, which is going to give me 6. If we plug in x equals 2, well, 3 squared is 9, times 2 is 18. And in a similar manner, we can plug in negative values. Okay? If we plug in negative 1, we have 2 times 3 to the negative first power. Well, we need to make our exponent positive. We'll bring him down to the denominator, and we get 2/3. If I plug in x equals negative 2, then I have 2 over 3 squared, which is 2/9. And that will be a sufficient number of values to plug in there. Last but not least, before we graph these guys. All right, notice if I look at my general exponential form, the number in front of the base here is 1. Okay, so for example, it'll make entire sense when we plug in x equals 0, anything raised to the 0 power is 1. All right, now let's think about something real quick. Okay, notice that the base of my exponential is between 0 and 1. That means that my function is decreasing. And let's look at what happens when we plug in various values. If I plug in x equals 1, well, 1/2 raised to the first power is 1/2. And I'm actually going to write this as 1/2 to the power of x. I like dealing with fractions as opposed to decimals. It's totally cool if you guys use your decimals. Okay, if I plug in x equals 2, well then I'm squaring 1/2, and 1/2 times 1/2 is 1/4. So notice, as my x values are getting larger, my function values are getting smaller. That really matches with what we're doing. Alrighty, let's plug in -1. Well, 1/2 to the negative first power. Recall our properties of exponents. That's the same thing as 2 over 1 to the first, which gives us 2. If I plug in -2, well then I have 1/2 to the negative second power, which is equivalent to 2 over 1 to the second power, which is 4. All right, now what I want to do is look at these graphs and make some comparisons. So, let's see. I'm just going to erase this so we have a little more room here. Now, once I graph these, we're going to look at trends and then make some generalizations. Okay? So, let's keep consistent with our colors. If I graph 3 to the x power, well, it goes through 0, 1. When x is 1, y is 3. When x is 2, we're all the way up at 9. So 3, 4, 5, 6, 7, 8, 9. Wow, that's growing. And when x is -1, we're at 1/3. -2, we're at 1/9. And that's my graph of y equals 3 to the x power. All right. Now, let's look at what happens when we graph 2 times 3 to the x power. Again, we'll plot our points. Now we go through 0, 2. Wow, we go through 1, 6. 2, 3, 4, 5, 6. And 2, 18. I'm not tall enough to get there. And then in our negative direction, when we're at -1, we're at 2/3. When we're at -2, we're at 2/9. Notice it's the same basic shape, okay? What we've essentially done is doubled our graph here, okay? And last but not least, we have 1/2 to the power of x. Again, that goes through 0, 1. When x is 1, we're at 1/2. When x is at 2, we're at 1/4. So it goes down to the downward direction there. And then if we plug in -1, we're up at 2. -2, we're up at 4. And there's our graph of y equals 1/2 to the x power. So some things to notice, okay? I would like to summarize some of these because it's pretty interesting. Alrighty, let's get this gone. In general, given y equals a times b to the power of t. Well, notice this a is our y-intercept, okay? For example, all you have to do is set t equal to 0. If you set t equal to 0, this term becomes 1, and a times 1 is a. So, we always know that these graphs go through the ordered pair 0, a. All right, notice something else. When my b is greater than 1, in both of my examples here where it's 3 to the x and 2 times 3 to the x, okay, this stays consistent. When b is 1, we have exponential growth, okay? And one thing that you'll see is that the larger value, let's say the larger B is, the faster it'll grow. And similarly, if B is between 0 and 1, we say it decays or it decreases. And the smaller value of B, the smaller B is, the faster it falls. Okay? Now, some other things that I would like to mention pertaining to the general graph of an exponential function. Okay, some things we like to talk about whenever we talk about new functions are domains, ranges, any x-intercepts, any y-intercepts, and then any other really interesting things pertaining to our graph. Okay, so let's talk about the general domain of our exponential function. When we talk about the domain, we're asking, are there any restrictions on our inputs? And I claim no, there's no restrictions whatsoever. We can see by our graph that x can take on any value. We can also look here and say, well, we can plug in positive numbers, we can plug in negative numbers, and we can plug in 0. So my domain is all reals. Okay, if you want to write that in interval notation, it's from negative infinity to positive infinity. Okay? Next, let's talk about our range. The range are our function values. Are my function values here ever negative? No. Notice that they're also never equal to 0. So we get really, really close to 0. I mean, for example, if we have 3 to the x power and we plug in x equals 100, or negative 100, I claim we have 1 over 3 to the 100th power. Well, I mean, that's essentially for all intents and purposes 0, but it's not actually ever equal to 0. So we say our range is from 0 to infinity. Notice I have a parenthesis next to my 0 because we never actually take on the value of 0. Okay, let's talk about that for a second. Okay. When we want to talk about whether or not there's any x-intercepts, well, I claim by saying we never take on the value of 0 in our range, there are no x-intercepts. Because let's look at this. For what values of x could we get this thing equal to 0? I claim there's no values of x. Okay, so for example, if we look at 2 to the x power, if you plug in a positive number, you're going to get a positive number. If you plug in 0, you're going to get 1. And if you plug in a negative number, yeah, it's going to get really, really, really close to 0, but it never is actually equal to 0. And our y-intercept, we said, is 0a. And notice if we just have y equals b to the power of t, then it's just 0, 1. Okay? Now, the one other concept that I want to bring up to you, because it's something that's important to think about as you move on, especially if you're heading over into calculus or any trigonometry. Okay? Notice with my exponential functions, as x gets really large or really small, depending upon the direction we're going. So the way we say that is as x goes to positive and negative infinity, notice that my function is going to 0. Okay? Now, when b is between 0 and 1, it turns out as x goes to infinity, my function goes to 0. Notice for where I have exponential growth, it's true that as x goes to negative infinity, my function goes to 0. This is a really important idea. Okay, so this is where we have exponential decay. Notice as my x values are getting really, really big, my function values are approaching 0. They never actually equal 0, but they're approaching it. And similarly, in both of our graphs where we have exponential growth, notice as x goes to negative infinity, in other words, as x gets really small, my function values are approaching 0. When that sort of thing happens, you have what we call a horizontal asymptote. Okay? So you have a horizontal asymptote if, as x either gets really large or really small, your function values approach some number. In this case, it's 0. All right, so let's look at a couple of different graphs here. And we're just going to make some general comparisons with these graphs. Okay, so here we go. All right, this is the point 1. And what I'm going to tell you is the graph of f of x, which is 0.7 to the power of x, g of x, which is 0.8 to the power of x, and h of x, which is 0.85 to the power of x, are in this figure. And what I would like to know is, can we match these formulas with each of these graphs? And I claim that the answer is absolutely. Okay? Again, these are relative to each other. Okay? There's a couple ways you can look at it, and they're actually equivalent. One comment that I made prior is, remember, the smaller the value of b, the faster it falls. Now, why would that be the case? Well, think about it. What is this decreasing by? Isn't this decreasing by 30%? This guy's decreasing by 20%. And this guy's decreasing by 15%. So this is going to get smaller much faster. So I claim then this guy must be f, this guy must be g, and this guy must be h. Okay? All right, one other graph that I'm going to draw here is as follows. And this is going to be not necessarily a matching one, but again, looking at general trends, because to me that's what's really important for you guys to get out of this section. Alrighty, so that's my graph C. This is my graph A. That's my graph B. And then my graph D is this guy. Okay, now what we're going to assume is that the equations for A, B, C, and D can be written in this form. In other words, we're making the assumption that they're all exponential functions. And what I want to do is just answer 4 questions. Okay? My first question is, which function has the largest value for A? Okay? What does A give us? A gives us our y-intercept. In other words, what we're asking is which graph crosses the y-axis at the largest point, and I claim that's my graph D. All right, now I will ask which two graphs have the same value for little a. In other words, which two graphs cross my y-axis in the same place, and I claim my graph A and my graph B right here. Okay. Which graph has the smallest value for B? Well, clearly the smallest value are going to be the ones that are decreasing. And remember, the smaller the value, the faster it decreases. Again, because that rate at which it decreases must be greater. So I claim D. And last but not least, we will ask which graph has the largest value for B. Well, what we're asking is which graph is growing the fastest? And I claim that's graph A. All right, so before I close this section, what I'd like to say to you is it's really important that you know the general vibe of how these exponential function graphs work. I'm going to be coming back to them soon enough because we're going to be interested in talking about the inverses of these functions in our next chapter. Okay? So that's why notice most of the examples I did are just really more gleaned toward gaining intuition as to what the various effects of the values of A and B have on the graphs of our exponential functions. So that completes section 4.3.